This is video 5 of week 2's lecture series on probability basics. So we just went over some basic concepts of probability or rules of probability. Now let's consider the situation in which two events are not mutually exclusive. That is, they can occur together. So the probability of A or B is therefore not equal to the sum of the individual probabilities. And an illustration that Paul provides is a situation in which we're in a field where there's oil and gas, but there may be some locations where there's both oil and gas. Okay? So the whole field of study is, I'm going to outline this field of study. Now, this is a Venn diagram, and it's useful for illustrating cases like that. But we can imagine this represents a geographic area, and the oil is contained in an area of this circle on the left. The gas is contained in the area of the circle on the right, and of course they overlap, as you see. So the probability of oil is the area is, well, it's equal to 0.18 plus 0.12. That's 0.1, that's 0.3. The probability, the probability of gas is 0.24 plus 0.12, and that's equal to 0.36. The probability of oil and gas is equal to 0.2. That's the area of overlap. And the probability of oil or gas is equal to 0.18 plus 0.12 plus 0.24, and that is not equal to the probability of oil plus the probability of gas. Right? The probability of oil plus the probability of gas would be the area of both circles, but since there's overlap, the probability of oil or gas is smaller than the sum. And what I forgot to write down is everywhere outside the circles, the probability of nothing is 0.46, because 0.46 plus these numbers gives 1. So the more general description of the probability of A or B would be the probability of A plus the probability of B minus the probability of A and B. And that's a more general rule for describing the probability of A or B. So now let's move on to conditional probability. We'll keep that diagram here. So conditional probability. And I'd like to define what a conditional probability is. So we'll use this symbol here, meaning the probability of A given that B has occurred, or B is present. I said has occurred, and actually Paul Wessel writes this in his notes, but there's no time in this implied by this symbol. It just means that we see that B exists. So given that B exists, what is the probability of A? Oftentimes people refer to B as the evidence. So for example, if the butler is a suspect in a crime corresponding to A, what is the P with the vertical bar B? The conditional probability of A given B describes the probability that the butler did it given that his footprints were at the scene of the crime. So the evidence is footprints, so what's the probability that he did the crime? So the evidence gives some added information to the assessment of probability. So next I'd like to write out two forms of Bayes' basic equation. So the probability of A and B is equal to the conditional probability of A on B times the probability of B. Okay, the probability that both A and B are occurring depends on the probability of B, and given that B has occurred, we have to multiply that by the probability of A given that B has occurred. Another form is, I guess, we can write the same thing out. Okay, so the joint probability of A and B occurring is equal to the probability that B's occurred given that A exists times the probability of A. So those are Bayes' basic equations, two forms of Bayes' basic equation. And from that, using that, we see that the probability of A given B is equal to the probability of A and B divided by the probability of B. Okay, and that came from the first equation. And by combining the second equation, we can derive Bayes' theorem, a form of Bayes' theorem, which says that the probability of A given B is equal to the probability of B given A times the probability of A all over the probability of B. So these equations are central to Bayesian inference or Bayesian statistics. So that's an introduction to that. Now let's look at an example here. And so for example, I didn't really leave myself enough space. Okay. So let's use the concept of Bayes' equation to estimate the probability of oil given the evidence of gas. Okay? So since we see gas, we know that we're somewhere in the gas circle here. We've landed our hole someplace in here. So, and let me go ahead and draw the whole field of prospecting. So the fact that we're in the gas circle means that we have a different probability of finding oil than if we were just anywhere in this space. Okay? So maybe you can see this visually, but since we're in this gas circle, what's the probability if we were to sort of randomly put our drill hole anywhere in here that will land also get oil? Okay, so and feel free to stop the video and think about what that probability is. But I'll go through and write it out. So as we said before, oops. The probability of oil given gas is equal to the probability of oil and gas divided by the probability of gas. Okay, so oil is A and gas is B. The probability of oil and gas is the area of overlap, 0.12. And the probability of gas is just the area of the gas circle, and that's 0.12, that's 0.36. Okay? So you can perhaps now intuitively see that's the area of the overlap divided by the area of the gas circle. Okay, so that's an illustration of conditional probability, and we'll continue on with that. So that's when A and B are not mutually exclusive. What if A and B are completely independent? They're independent of each other. Okay, so that must mean that if they're independent, that the probability of A given B is just the probability of A. The existence of A does not depend on B, so the probability of A given B is the same as probability of A, and likewise the probability of B given A is simply the probability of B. And the probability of A and B is simply the products of probability of A, probability of B. Okay, that's just okay. You can derive this following the previous equations that we used. And in general, for n independent events, the probability of all of them occurring at the same time is the product of their individual probabilities. Okay. So, for example, what's the probability of getting 3 ones in a row of when you roll dice? And that probability is equal to the probability of well, a 1 in one roll, a 1 in the second roll, and a 1 in the third roll.